Good evening, everyone. My name is Eric Flesch, and I'm the director of the Mining and Rollo Jameson Museums. And welcome to this first of 7 presentations as part of the 2023 Winter Lyceum. Today is the 19th day of February, 2023, and I'm broadcasting from Platteville, Wisconsin, home of the world's largest letter M in the heart of the driftless area, in a special place known as the Upper Mississippi Valley Lead and Zinc Mining Region, where the Badger State was born. Founded in 1965 by the city of Platteville, the museum brings to life a rich cultural heritage rooted in local history, a tradition of science, technology, engineering, arts, and math, and a celebration of the pioneering spirit, which we recognize to be the living human spirit of ingenuity, inquiry, enterprise, and development. This year's Winter Lyceum promises to be a truly electrifying series of 7 presentations. The subjects of the talks range from adaptive reuse of historic mines to high-tech battery manufacturing to organic farming to creating artistic geometric abstractions from nature. But they all share a theme, and that is the subject of energy in the context of our driftless area landscape and current events. I invite you to stay up to date on museum programs and to support current initiatives online at www.mining.jameson.museum. It's my great pleasure to welcome you this evening to enjoy a talk by archaeologist Dr. Timothy Scarlett titled Abandoned Mines as Tools of Economic Revitalization, Converting Liabilities into Assets for Post-Mining Communities. I'd like to thank all of you who have registered to participate live today, as well as those who may be watching a recording of this event from our library of virtual programs. I extend a warm welcome to current friends of the Mining and Rollo Jameson Museum's members and donors. And I, of course, would like to thank the sponsors whose financial support has made this program possible. A&W Restaurant of Platteville, Claire Bank, Edward Jones Financial Advisor, Bob Hundhausen, Inspiring Community, State Farm Agent Jordan Holthouse, and Tricor Insurance. And now, before we begin our program, I'd like to invite you to participate in a question and answer session and a short survey at the end of this evening's presentation. Because we're a very large online group, in the interest of time, I'd like to invite you to type out your questions as they come to mind and to submit them via the Q&A function at the bottom of your screen during the talk. And then at the end, the speaker will answer as many of the questions as he's able in the order in which they are received. So I'm now pleased to introduce tonight's speaker. Dr. Timothy James Scarlett grew up in rural Bucks County, Pennsylvania. He earned his bachelor's degree from the University of Arizona in Tucson, my alma mater, and then his master's degree from Boston University and his PhD from the University of Nevada. Tim joined the faculty of Michigan Tech in the Industrial Heritage and Archaeology program in their Department of Social Sciences in 2001. And he's an associate professor of anthropology there and deeply committed to a dramatically interdisciplinary approach to public archaeology. His diverse community of collaboration includes students and faculty in energy and environmental policy, material sciences and engineering, chemical sciences and engineering, material science and engineering, geological and mining engineering and sciences, and the College of Forest Resources and Environmental Sciences. Please join me in welcoming Dr. Timothy Scarlett.
Thank you so much, Eric. And I'll start by going ahead and setting up the screen sharing and get right underway. I'm really thrilled to be speaking to the community there in and around Platteville. I've had an opportunity to travel through your mining heritage region, and which shares many similarities with where I live, and it's a beautiful place. And I think that everyone will have some real interest in the kinds of work that we've been doing that I'm going to talk about. I want everyone to understand that I'm excited to talk to the residents and the communities around mining and post-mining towns, in part because I've done this presentation now a couple of times, versions of this for people in government or people in archaeology or people in different institutions. And they they don't necessarily have a very good understanding of what it means to be a resident in a post-mining community. So I hope that I've tweaked things here to suit your interests. And I want to acknowledge a little bit about our history. Many of you probably know about the history of Michigan's Upper Peninsula. We have an iron mining region, and we have a copper mining region we call the Copper Country. Both of them in the Lake Superior mining districts. Michigan's copper mining region is the oldest continuous metallurgy undertaken by humans in the Western Hemisphere. An emerging study is pointing that this goes back as much as 9,000 years or more. Essentially, the glaciers melted and people began using the copper resources as they discovered and experimented with them. It also then became the host to the first industrial mining boom in the 19th century in the United States. It occurs while the lead and copper countries are both being exploited in antiquity, and their early developments of those mines. The really heavy invested rush for copper in the copper country was unparalleled in American history. And it became one of the most important copper districts in the world during the time that it operated through its boom. And as such, I want to point out that my own campus is on the ceded lands from the Chippewa homelands that were ceded in the Treaty of 1842. And for several centuries, the members of those communities have been the managers of this land and the managers of this metallurgical tradition and its lands and waters. And as such, they are important participants in this process as we think about the nature of post-mining environments. And I know that you all understand what it means to be in a post-mining community. Their post-mining communities are different all around the world. They are not one thing, but they do share some commonalities, and I know these will resonate with many of you. They have problems with sustainable economic development and attracting investment following the collapse of what is usually either their single big employer or their single sector industrial employer in a particular mineral. They're often struggling with cultural renewal or the need for demographic stability or fighting brain drain because their youth are leaving town for good jobs. They often have legacy infrastructure, just this overbuilt large volumes of buildings and things they can't maintain, too many cemeteries and churches for them to manage. They have maintenance backlogs. These communities are almost always facing environmental legacies of mining and smelting and milling and the associated industries that supported those activities. And they're also struggling because they were at one time, they were the node within the systems of support that kept them operating, the energy systems, the transportation systems. And now they are on the periphery or the margins as they've transitioned to post-mining communities. And those old infrastructures have decayed or not been maintained or not updated. And for every one post-mining community that might be a Park City, Utah, or Vail, Colorado, there are dozens and dozens that don't have the same environmental assets that they're able to capitalize on. And so mining communities like yours and mine are these incubators of experiments as people are struggling to figure out how to make this work. And as you all know, they're not simply victims sitting there where all these things are happening to them. They're actively working at City Hall and in community organizations like your museum and your heritage organizations to figure out how these things can happen. And I know there are lots of parallels between my experience here in the Copper Country and yours down there. Communities are struggling. We here in the Copper Country, just as one example, pay the highest electricity rates in the United States, in the continental United States. We're comparable to the most expensive rates in Alaska and Hawaii. Our electrical system, UPCO, is owned, it's an investor-owned company out of the United Kingdom now, located overseas. And people in my community struggle with the nature of how expensive electricity is, because it cuts across all of our efforts at trying to improve our lives and our communities, because electricity and energy underlie everything, right? Now, communities like mine and yours are constantly working with all kinds of different agencies at the state and federal level in trying to develop plans to improve their situations. And I know that you have been participating in many of those, thinking about geoheritage and the way that tourism can attract people, as an example, in mining heritage tourism. And these things are being done around the world. There are all kinds of experiments with transitioning post-mining landscapes to different kinds of heritage assets within their community. But almost always the scale and the scope of mining landscapes and problems are so daunting that it's very hard for local people to deal with them by themselves. They lack the expertise, they lack the capital, and they lack the connections to facilitate these transformations. So at Michigan Tech, my colleagues and I in the Department of Social Sciences found this question about mines and energy in post-mining in communities created this collision between our existing interests in industrial heritage and archaeology, where we've been studying mining for many, many, many years, and in environmental and energy policy. And we have many people across campus who work on different aspects of energy and mining and things like that, which we could gather into the KETL, we call it, or the Keweenaw Energy Transition Lab, to work on projects. And we're going to talk about more in a minute. But we think of these things because they're what the National Science Foundation would call a wicked problem, right? They're incredibly complicated, big problems that are hard to solve. If they were easy to solve, somebody would have solved them already, right? They're challenging. And as we transition from energy to mining, I want to set the stage for you to think about the particular topic for today. Energy in the United States 150 years ago was distributed small scale, little grids growing up around industrial operations or urban places, and then cultivated through policy and intentional spending, grew to be a national grid that's incredibly complicated. When you plug in your power, your hair dryer in the morning and turn it on, the entire electrical grid in the region instantaneously balances itself. Many, many times a second, it's spontaneously balancing itself. In a market where people are buying and selling the energy in a futures market simultaneously with not-for-profit cooperatives cohabitating on the energy grid with for-profit companies, and you have transmission companies and you have consuming companies and associations, it's an incredibly complicated system. But as it evolved, it grew to be centralized, large-scale producers of power, pumping it out into the grid that then enabled individual consumers. Excuse me. And one of the challenges of that immediately became apparent, that the behavior of people doesn't match the behavior of power plants. If you're running a nuclear power plant or you're running a coal-fired power plant, the best way, the most profitable way to run that would be to optimally operate it at your energy invested to the power you're getting out. And you can tweak it a little bit over time. But if you imagine a graph in your head, you want it to be an even, highly efficient system. The problem is that humans don't demand energy that way. We all wake up in the morning and we turn on our coffee pots and our hair dryers, and the demand for power goes way up. And then it goes through a peak over the course of the morning and the day. When people get into the office, the power actually declines for residential consumers because they're not at home and the lights are off and the house is, the sun is out. We're not running our power. to lighten rooms. But then nighttime comes, and as it happens again, power spikes, and people need power between 6 o'clock and 11 o'clock at night. But then everyone goes to bed and they turn their lights off, and again, the power demand drops. Well, if you're running a nuclear power plant, you can't just ramp it up all of a sudden and generate more power and then cool it down all of a sudden and cut power. So the solution to that in our big centralized grid was to create energy storage facilities like Ludington in Michigan, Ludington's pumped hydro storage plant. When you don't have a lot of demand, you take the extra energy from the nuclear power plant or from the coal power plants or whatever power plants, and you pump water uphill where it has potential energy, and you store that water until there's a demand for more electricity than you're currently providing from your big centralized plants. You then reverse the pumps, open up the head gates, let the water flow back down through the turbines, and you generate power, pump it back out into the grid, and sell it. This system of pumped hydro storage takes really mature hydropower technology and uses it to create batteries. The Ludington plant, like many plants around the world, were built with the build out of nuclear technology in the 1960s and 70s. It's now just celebrated its 50th anniversary. The companies that have been operating it profitably all those years, they just refit all the turbines. It's going to operate another 50 at least as a profitable facility. And it operates in a pretty intuitive way, right? You use energy to raise water, and then when you need energy, you drain the water back down. The trick is that as we built out these facilities, the ability of companies to build large pump hydro storage facilities kind of waned in our big electrical grids. And the reason was, if I back up here to the picture of Ludington, those of you who know the geography of Michigan know about this area of Northwest Michigan. You could think about what's around here over around this facility. Sleeping Bear Dunes National Monument, for example, and a lot of important lakeshore and green space. And in that time, since the 1970s through the 1980s and 1990s, the 2000s, as land use patterns changed and grew, the green space of areas where you have elevation overlooking bodies of water became very, very valuable. Open space and green space and agricultural land became valued for more than just the potential to store electricity, such that people thought that pumped hydro storage wasn't the best, highest and best use of this land. And more to the point, the environmental impacts of pumping large volumes of water up out of water systems or down into water systems and manipulating water like that, people became increasingly uncomfortable with the environmental questions about the impact on surface water flows. Now, as the energy system evolved, what that meant was that we needed to find other ways to solve these problems of fluctuating demand versus the core supply. And we did that through taking old plants and partly retiring them, or building new plants that are like natural gas powered plants that we call peaker plants. And they're operated, they exist just to run a couple hours a day. When demand peaks and you need to fill in the extra demand, we'll run a peaker plant and it'll pump energy into the system. And doing that profitably in shaving off peaks, if you will, is technically called arbitrage. You're buying low and selling high like any other kind of commodity. And those peaker plants then became a feature of our system that got built into the network as it grew. They're also the least efficient system. Just like you drive your car, if you stomp on the gas pedal to 0 to 60 as fast as you can, you're going to burn a lot of gasoline, right? If you have a power plant that you're turning on to run and then turning off, it's not going to be as efficient. But I also need you to understand that these plants do other kinds of things besides just that. They also provide all these electrical services for shifting loads around between the different electrical grids, parts of the grid, balancing the system, regulating frequency on the grid, or what we call black start. When there's a blackout and you have to restart the electrical grid, you can use one of these facilities as a black start to get the electrical grid up and running again. So we've evolved into this incredibly complicated electrical system in the United States that has got different kinds of operation in different regions. We here in the Midwest are all part of MISO as a transmission region. There are different rules, different things in place in each part of this network. It's really incredibly complicated, and I'm grateful that I have colleagues who are professionals in this. But we're facing another challenge, right? That is that the technologies of generation have changed, in addition to our consciousness about the costs of carbon. So we're undergoing an energy transition now in the world, where we are seeing a shift from these centralized big production facilities to potentially decentralized small producers of things like rooftop solar, where or individual small wind farms, these different kinds of facilities. MISO, our electrical group, is predicting that by 2029, we're going to add 3.5 gigawatts of intermittent solar and wind electricity to our grid. And right now, we don't have the capacity to handle that. The primary, let's look at why that's a problem, right? The problem is not whether you are a follower of the discussions about climate change or you're unconcerned with climate change. Really, this doesn't matter, because what's happening is that the economic pressures, my colleagues have shown me, the economic pressures on solar and wind are both such that it's becoming cheaper and cheaper and cheaper to create panels. The panels are becoming increasingly efficient at a rate where they are now rapidly a self-sustaining, clean kind of energy production that doesn't produce particulate matter and it allows people to set themselves up as independent from the electrical grid. It's going to transform the global electrical system. Whether or not one pushes that transformation or rushes that transformation because of concerns over carbon. And it creates this problem in the grid, which is like our old problem, but even more exacerbating. Because now when we have more and more and more solar panels out, what happens is that more and more solar electricity gets generated during the daytime when municipal power consumption actually drops down. And you have a mismatch of when energy is being generated from when energy is being demanded. But on a sunny day, as we get more and more and more solar, it's depressing the power, the value of that power to the point where producers in the bottom of the duck curve here on the graph, producers in the green area have to pay people to take the electricity from the generators because electricity has to be stored or used. Otherwise, it just goes away, right? What you need is to be able to capture that energy and then bring it up to the red area on the duck at the head of the duck when, again, people come home from work each day and there's a demand for electricity. So we need batteries. We know that right now the US has about 23 gigawatts of capacity for energy storage. That's going to have to increase by 2050 by at least 80%. The amount of energy that's going the amount of energy storage that's needed is absolutely blows your mind as you look at this situation. Because you need to be able to balance that generation and demand. You need to be able to do all of the complex engineering on the electrical grid, and you have to have energy storage. Everyone has known this need for energy storage was coming. Everybody has been aware of it. And they've been, as we say in politics these days, kicking the can down the road for decades. No one could build new large-scale storage facilities. And we kept hoping that there was going to be a battery solution like the Tesla power walls, and that you'd be able to build these facilities with, solve them with a simple problem. Solve the problem with a simple solution. The problem is that chemical batteries are never going to be available at the scale that we need them to solve this problem, and the ecological footprint of creating those chemical batteries to do this solution would be catastrophic. Plus, chemical batteries have a limited lifespan and need to be renewed. And even once we can recycle them efficiently, there'll still be this constant need for renewing those batteries. Yet we have a technology that we know works. It's incredibly clean, yet we can't build them. So we have the greatest technical problem facing the energy system, which is one of the greatest problems, wicked problems of modern society. And we can't solve it with the most efficient solution that we have. Well, what if you put a pumped hydro storage facility underground? We're not the first people to have this idea. When my colleague Roman Sidortsov came into my office as an energy scholar to ask why people in the UP don't use hydropower, we had a conversation that actually stretched into a couple of hours. We were drawing on the whiteboard and we were talking about how big the underground mines are, and what if you took an entire pumped storage facility and put it underground, isolated from the local water system. This was the first little sketch I made in the animation of a local mine, the Quincy here, with tourists on level 7 and bat habitat on level 1 or level 7. And the way you could potentially design something where you could have an energy storage facility underground while still having tourist access, still having a historical museum on the top. What are the possibilities of this? And we started really talking about the Quincy to get us going. And we took this idea, started doing some background research, started attracting people from all over campus, from our colleagues in mechanical engineering and geological engineering and in ethics and all over the place, working on this issue. And as we were exploring the question, we found other people have talked about it, right? What most people out there don't understand is that a lot of these mines are huge. And the capacity of those mines is tremendous, but we had no way of knowing what the capacity was. We found people had looked at this question in the past. In the 1950s, the Department of Defense thought they could use nuclear bombs to create underground cavities to build these systems so that they would be nuclear bomb proof energy storage systems for military bases. But in the past, when people looked at this idea, they had a very narrow view of techno-economic questions. Is it technically possible, and how much would it cost, right? Well, we took this question and we gathered our partners and we wrote a proposal to the Alfred P. Sloan Foundation. And the Sloan Foundation gave us a small grant to develop some collaborators and do a study of saying, like, pick a real place and just see what it pencils out like, and use your broad perspective on value. And so we began looking around, and we needed a partner who had a mining heritage institution. And then we needed a partner in energy. And we found that with good friends at WPPI Energy, who had worked with Michigan Tech before. And we looked at WPPI Energy's service map, and we found that they have service in a little area of Michigan up in the community of Negaunee, in the area of Negaunee and Ishpeming. This is in Michigan's Iron Region. And so we said, okay, well, let's go to the community there in Negaunee, and we'll talk to them about some of the historic mines in their area and see if they want to partner with us. And sure enough, they did. I'll explain. This is a slide actually of Ishpeming, the neighboring community to Negaunee. And this is actually the Cliffs Shafts Museum, another mining heritage museum and site. And as all of you are familiar with there at the Mining Museum and Rolla Jameson Museums. And we found them as a willing partner in Negaunee, and the folks in the mining heritage community there to be very enthusiastic and supportive, even though we were doing this just as COVID hit and we had to shut down and slow down our analysis. What we did immediately was save the company probably $3 million. Not that this is a real development project, but in our hypothetical development, because we went to the town and we said, we've been looking at this, thinking about this, and I've researched your mining heritage, and here are some mines. Here's a mine I think we could study in your community. And the city leaders talked with us, and they said, this is a really interesting idea, and we'd love to talk to you more about it. But what we need you to understand is that you should not go anywhere near that mine. That particular mine was the scene of a tragic mining accident. The miners were not recovered, all of the miners' bodies were not recovered. That is a tomb in this community, and you should not touch that. However, you should go look at this other mine called the Mather Mine. And so we said, sure, okay. We went and we started looking at the Mather Mine. Now, as all of you might imagine, in the United States, mining is not controlled by one central authority. And so when it comes to things like the records of mining, they're held often by local institutions like the Cliffs Shafts Museum. And those institutions are municipal or they're not for profit. They're doing the best they can with the resources they have, with all the problems we identified earlier, right? They're trying to balance prioritizing the overbuilt infrastructure they're trying to preserve with community memory. They're trying to do economic development. They're doing the best that they can with the resources they have, and they've been the lighthouse keepers for mining resources in America for the most part. As we investigated the Mather Mine, the folks at the Cliffs Shaft welcomed us into their archive and helped us find resources. And there were state agencies that helped us as well. The Mather Mine is an interesting site. The new high school there in Negaunee was moved up there after the mine closed in the early 1970s. They adaptively reused some mine buildings as part of the high school. The mine is connected to the underground workings. The mine is connected to the high school through the underground workings in an area that has been made completely secure through brick and concrete so that high school students can't get into the mine. But it is interesting that it sits directly on the property. As we looked at that mine, we were then able to undertake our research, and I turned it over to our colleagues and our collaborators. And I'm going to explain this in more detail in a few minutes, but this is a scaled schematic drawing of what might happen, of different ways you could design an underground facility in the Mather Mine storing electricity. On the very right-hand side of this diagram is Ludington, Michigan, the pumped storage facility in Ludington. So it has actually the infinitely large Lake Michigan at the bottom and about 111 meters of head, and then about 102 million, cubic meters of water in it. Now, the Mather Mine, unsurprisingly, if you built surface ponds or if you used the lower levels in different configurations, would hold somewhere between the 13,000 or 13,500,000 cubic meters of water, or in a surface pond might hold up to 33 million cubic meters of water. But the head would be 10 times that potential at Ludington. So you have less water, but you have more vertical feet. And what that translates to is that the Mather Mine has as much capacity or more than Ludington to store electrical energy, to the point that the Ludington mine, if it were used at full capacity and we were to pretend it was a hydropower station, it's not, it's a battery, but it would be the 6th largest hydropower station in the world. And I will pause to make sure that everyone heard what I said there. The 6th largest in the world. Once fully charged in this grand facility that would be so big no one would ever build it, this mine alone could power all of the Marquette metropolitan region for more than half a year, based on our analysis. The outcome of this, we are not alone in doing these studies. As I said, people realize the possible insight and capacity of these mines in solving this critical problem everywhere in the world means that all around the world, people are looking at this question of adaptively reusing mines. The Finnish government is investing. They're probably going to be the first ones to actually build a mine as a pumped hydro storage facility. It's happening in Australia. It's happening in South Africa. It's happening in Sweden. It's happening in Germany. This is happening very, very quickly because it is one of the greatest challenges we face, and it's potentially an elegant solution to that problem. Now, what I want to explain in a little more detail is about what that means for all of you, because the mining communities have these records like these from the Mather, the engineering drawings that allowed us to say, well, let's assume with no new construction, we're just going to fit this thing in the existing infrastructure within the mine. We could design that in our engineering teams. We could look at the way in which the mine was built out over time and the different mining techniques used from the technical reports, block caving system in this case. We could lay out those maps and develop really accurate understandings of the capacity of the mine and how it changed over time. We were able to digitize those and create three-dimensional models that we could then take those models and turn them over to the design team to talk about what are likely possible scenarios. Then back to this figure, these scenarios are then based on the most accurate possible predictions or measurements that are available. The only way to get better measurements would be to drain the mine and go down there and look, right? So when I tell you about our outcome from this study, and I've shared the link for downloading the report to Eric. Eric can share them with everyone in the chat. You can go through and look at the report and look at all the technical details. I'm not going to belabor the point here. Our team did incredibly sophisticated work, I think, with the time and the resources that we had. They did highly accurate CapEx measurements. We looked at dynamic expectations without doing a full grid integration study. We looked at the dynamic aspects of buying and selling electricity in the market under actual times. And we were able to show that under some conditions, even without taking advantage of every possible financial incentive, and without looking at new incentives that hadn't been created, and taking very conservative estimates of cost from examples in mining engineering and hydropower development. Under certain scenarios, these things make money on their own currently. They're more complicated to design and build, and each one of them has to be different, unlike a preferred business model where you design one Walmart building and then you build 2,000 Walmart buildings on that plan. But they are potentially really elegant solutions to this challenge. I'm going to skip over a couple of items here, but we were able to include water quality analysis as part of this because water quality is an obvious concern. And we were able to show for Mather, in this case, water was not an issue. But you all in residents of a mining town know that in terms of mining, the water runoff from mines and water treatment is a really sophisticated existing technology system. We know how to treat mine water. The the EPA just approved discharges from Berkeley Pit in Butte, Montana, back into the water system, one of the most polluted places on Earth. We know how to treat water. It's not a technical challenge. It's who's going to pay for it. That's the challenge, right? So we said, what if you design this system in a way where it treats the water while operating and as a part of doing business? Then any water that is discharged from the mine, even though it's a closed loop system, there would still be some discharges. That water will improve local ecosystems, and it will continue to do so over the lifespan of the operation of the mine. Well, how do you put financial value on that, for example? This is one of the things that we learned from Mather, and we turned then to take a look at the national picture of what was possible. We compared existing mine data locations, which I'm going to let this lie because it's complicated, but you can see metal mine locations here from the USGS database in our region, including the lead and zinc districts and the copper and iron regions. We compared those against existing electrical infrastructure, against potential solar energy and existing solar infrastructure, against potential wind energy and wind infrastructure, existing power plants and all those things, and consumer base loads and price indices. And we found that there's more than enough capacity in abandoned mines to build energy storage systems to solve all of the energy storage problems in the United States. Even if a fraction of those are deemed appropriate. Now, that said, and even locally here, this is a pretty well-known map about offshore wind power potential here in the Great Lakes. And I don't want to belabor the point, except to point out how close those bright red high-value areas are. The energy market has changed so dramatically in the last 10 years. The last offshore wind auctions were measured in the trillions of dollars of economic value. But what does it all really mean for you? These are things we'll continue to talk about after the slides as we just have discussion. What interests me is, as I'm talking to all of these people, that if you want robust agreement on the way we're going to solve these energy problems, and we're going to change our infrastructure in ways that people support, it means you should change the way you go about doing projects. Because mining towns and post-mining communities are not wastelands. Here, something I hope that strikes close to home. If I were designing one of these projects, the way the federal system works now, there are a couple of laws that regulate things, and it changes by state and by region, and it's very, very complicated. But in a nutshell, the way the system works, if you're a company, you need to come up with a plan, and then you approach the agencies, and the agencies then look at your plan. And if the plan isn't detailed enough for them to make decisions, they give it back to you. So the company develops a detailed plan, and then the agency says, okay, now you can start the process of talking to the public about your plan. And whether that's through the NEPA or the NHPA, the National Environmental Protection Act, or the National Historic Preservation Act, whichever one of these laws, there are a number of different laws that apply. All of them set up as a consequence of the way they work. The communities have to react to what the developers want to do. And that means that the developers, unless they choose to think about it ahead of time, aren't thinking about what these post-mining resources are in their communities. And like in my community, like in yours, the mines matter to people, not in some Pollyanna way where we don't understand the ecological challenges and things like that, but they matter as places, as landscapes, and as locations. People get married and they take their wedding photographs with the Quincy Mine hoist in the background. Our school children go to the mine museum to travel around and go underground and learn about the history of mining. These landscapes matter to people. This is a famous, this is a screen grab from a film I use as an example because it's a bunch of folks out here having a bonfire on a stamp sand, we call locally stamp sand. It's a mines tailing beach before it was reclaimed by agencies in reclaiming the stamp sands to deal with metals contamination. And that's a classic example of what people typically think of as an undesirable behavior. It's youth causing bonfires, causing problems, whooping it up out there on the beach. What's actually going on there? This is a scene from the film Where Soldiers Come From, and this is a going away party for 5 young men who were had just joined various branches of the military and were mustering off to Afghanistan and Iraq. And this is their community send-off out on the stamp sands. The sheriff is there, their parents are there. It's a community party at an event because you can't have a bonfire of this scale in the middle of a field in the summertime. The stamp sands are a good place to do that, right? people bum around, people do things in these places, and they matter to people. People have been using them for decades in cultivating heritage tourism and geoheritage activities to draw sustainable economic development from these landscapes. So planning for these changes as an energy company, if you're not paying attention and you're not choosing to engage with the communities, you're not going to realize any of this. Could you design a system to take into account the kinds of things we've been talking about? Absolutely, you could design it. Would it be the most profitable way to operate that facility? Well, maybe not. It depends. There's a lot of complexity in that analysis, but that's the kind of thing we can know because we've developed those multiple possible models for how the system could operate, how it could be designed. Could you use your system to reinforce cultural initiatives that matter to people in the community? Could you design it in such a way in collaboration with them where you're working together to dovetail all of those needs? As an example, here in the community of Calumet was a former major metropolitan region. Now it has 700, 900 residents as a village here in the Copper Country. And they have a number of important economic activities going on there, including some industrial manufacture of high-end electronics there at Calumet Electronics Company. One of the things that the community of Calumet had considered is whether they could use the geothermal energy from abandoned mines to provide HVAC, heating and cooling in their downtown. And the answer, the feasibility study that Michigan Tech did years ago, is absolutely. Technologically, this works wonderfully, but because our electricity rates are so expensive, the cost of pumping the water and operating the system makes it essentially about the same cost as staying with our current system for heating and cooling. But if the cost of electricity were to change, would that change the dynamics of a HVAC system for a municipality, for example? The answer is probably yes, but we don't know because no one's actually tried to run any of those numbers yet. Another example is that there are many other evolving technologies out there on the landscape which you should be aware of as a post-mining community. This is an example of binary geothermal, where this is about using underground energy, geothermal energy, not just as for direct heating and cooling through a heat pump, but actually using it to generate electricity. And it works under certain conditions. This is a demonstration plant operating in Nevada, operated by KETL here in the United States. Could you do that in conjunction with a push facility? Maybe. This is another technology system that's just reaching maturity. I actually mixed those up. That's the geothermal plant. This one is a compressed air facility, which essentially works like pumped hydro, except that you pump air down into a chamber where you build up a lot of air pressure when you have extra electricity. And when you want that surplus electricity, you then kick that back and it generates a bunch of power. It's less efficient than pumped hydro, but still profitable. And HydroStore, a company up in Quebec, built a underwater facility off of Toronto, where they pumped the air into bladders under Lake Ontario, and then they blew the air back out to generate power. It was a successful demonstration plant. They just signed something like a $700 million, $1 billion project agreement with companies in California to provide energy storage on the electrical grid there. So as you're thinking about what that means, what we're doing and where you're headed, it means that communities actually have the information often, either in oral history or in archives and documents, or a combination thereof, to design these facilities. The companies need that information, and that could give you a seat at the table. And I want you to understand the potential value of that. Billions of dollars in a problem. The federal government is throwing billions of dollars at solving this problem. that means that you as a community have time to think about, it is the time, excuse me, to think about your heritage of mining and your energy infrastructure, the heritage of energy, who benefited from energy regimes and who paid the costs for those regimes. When we talk to people in the community of Negaunee, among the things they would say is, I could support a project like this if it ensured the vulnerable people in my community got electric service, couldn't be disconnected in the wintertime, that we were protected. And then they would be willing to support the development of the project. Other people said, we would be willing to help this project if you could ensure us that you could demonstrate to us very clearly that water quality would be protected. Or if you could set up a program where it's at the high school, right? You could connect the technical training program in the high school with the facility where you're teaching kids about electrical energy and about solar power, and they're setting them up into apprenticeships, doing installations and maintenance. We'd be on board with this, right? You as a community coming to the table can bring resources and information available to companies. You can then potentially contribute in design, reaching collaborative designs that are exciting. When we did our final presentations in Negaunee, people's response were, how can we help? And our colleagues in the energy industry, when we talked to them about that, we were at a public meeting talking about an infrastructure project and people wanted to help us. They are stunned speechless. The last thing I want you to consider is that there's a huge fire hose of money being opened at this problem, but it has a timestamp on it because the problem needs to be solved. Industry will solve this problem. And once they have solved it, they will no longer consider these other solutions, even though they're more elegant. So now is an opportunity for post-mining communities to think, is this something we're interested in? Can this help us with the efforts we're trying to facilitate in revitalizing ourselves and renewing our communities? And if so, what would potential solutions look like that we'd be willing to participate in? So I appreciate all the time. I'm just a few minutes over, and I'm really thrilled to have had everyone's attention. And I'm happy to stay on and talk now with questions. I'm gonna stop sharing my screen so that I can see pictures again, but I'll switch back if I need to go back to any of those illustrations to answer questions.
Oh, Tim, that was wonderful. Thank you. It was so stimulating. All my neurons are just pulsing with lots of follow-up questions for you. All of us in the audience here, this is a great time if you haven't already. Start typing in your questions for Tim in the Q&A feature at the bottom of your screen. And okay, we've got one already ready, and then I've got a few on deck here while we wait some more to come in. So first of all, Mark has a follow-up question about the Mather B. That is, does the Mather B head assumption rely on a completely or nearly dewatered mine?
Yeah, that's an awesome question. One of the issues, dewatering is a big deal, right? And even in the mining industry, people don't dewater things for fun, right? It is expensive and time consuming, and there are environmental implications. The design that we had, we were assuming those different models, but all of them said, let's completely dewater the mine to build what we need to build. And then we let the mine fill back up. And because of the nature of the system, you can fill it back up with different kinds of water, depending on what you're doing. But then you have to have a maintenance level of dewatering, because water will infiltrate the mine, and there are steps you can take to minimize that. But it's probable that there will always be water coming into the mine until it recharges to the level of groundwater. So you'll have to maintain somehow through either putting in pressure walls and doors, or through occasional discharges. You'll have to maintain that level of water that you want for the facility, right? So that's an awesome question, because you could compare that with something like compressed air, underwater compressed air in an underwater flooded mine, where potentially, if we could build it this way, you could put all that stuff under there without draining the mine. You don't have to worry about the changing the structural integrity of the mine because you're leaving the water in place, which maintains the stability of the structure, and then operate the facility without having to dewater the mine. Maybe, right? No one's ever tried that before, but it's very possible. These are all existing technologies. We wouldn't have to invent anything to do them. It's just that no one's ever tried.
Well, I guess the million-dollar question is that I find myself wanting to ask, and maybe some of us in the audience are asking, is well, what about the historic mines of the Upper Mississippi Valley mining district, where we have a number of hand-dug lead mines, maybe around 50 feet deep or a little bit deeper, or we have some deeper zinc mines from the 20th century, but nothing like those deep mines that you have up there in the Keweenaw Peninsula or there in the Iron Country. There you had the same ore deposit that would be mined for more than 100 years with this huge permanent infrastructure overhead and thousands of feet deep. And our ore deposits here were smaller and less continuous. And what are some of the options for us and other kinds of mining districts? The different, where the scale is different or the depth are different, or the shapes are different, like we've got long so
those are fantastic questions. And it is one of the ways I describe this with people is that in some ways right now it's a choose your own adventure novel, right? The one of the greatest illustrations as we've become involved in this research and have colleagues now all over the world. One of the things we've realized is that, of course, many other countries in the world have much more tightly regulated history of their mining industry. And so they have, for example, an existing database. They can get on the computer and they can say, what is the deepest mine in this county? And they know the answer to that question. We do not have that answers readily at hand. The research group I'm in, we're working on compiling what we do know and then adding to that with other information. But in your example of these very shallow surface mines, like the lead mines, those are not necessarily appropriate for pumped hydro storage underground, right? But then the zinc mines, some of them may be large enough. We don't know the answer to that question yet because, again, no one's ever tried to run those numbers. And really, there's two separate questions because it is going to be, of course, technically feasible to build a facility in one of those mines. The question is whether it makes financial sense and it makes sense in terms of the power systems, the energy systems, right? Generally speaking, the investment that it would take to build one of these in a mine that you have to dewater and you have to build your infrastructure and put water back in and then you can operate it, those need to be larger scale. But if you have a mine where it is part wet and part dry, and you're able to use that to your advantage as is, a smaller scale mine storage might work in that situation for like a large industrial campus or for a municipal government. But again, no one's ever tried to pencil that out. It's just that the people have looked at the numbers over the years and they've made decisions based on sketches on that were sometimes quite detailed. Like in Minnesota, they did a very detailed study of this, but they did it in a way that was very techno-economic focused. And as an example, they never thought about what is the added value if you also take geothermal energy from the system, or what is the added value if you are doing water treatment and you're harvesting you're reclaiming the minerals from that water and then you sell those minerals. Right? That never occurred to anybody to think about that. What happens if you're, just as an example of, there are a lot of regions where there may be rare earth minerals that are now very valuable for the energy transition that they could harvest from mine water that they're reclaiming just as part of the operations of the facility, right? So the way the agencies and the energy companies are looking at this, it's as like MISO, right? Or as giant electric stuff. If you're a community, you might look at it from the perspective of, like what are the other kinds of values that we might take from this system, and let's pencil that out for ourselves and see what it looks like. And then maybe we'll have a conversation about a municipal facility, or maybe we would have a conversation with an industrial partner. As an example, you're seeing the evolution of the energy system where the storage is such a problem. Energy companies are building battery packs in high schools, where they put solar panels on the roof of the high school. They put batteries in the high school, and then the energy utility runs the battery pack as an energy storage asset, and the school gets essentially free or real discount electricity rates based on the use of that resource on their property. So the school has a benefit that's financial and electrical. And these are things that people are doing now in the country, right? The utility gets an energy storage asset that they can add to their portfolio. And that's just a battery warehouse, right? And as this evolves, those are the kinds of creative solutions that require activists to help make happen. Industry is not going to think of those kind of solutions on their own, not because, and I'm not blaming them. Their job is to find the easiest solution that requires the least investment, that's the most effective, and can be done as quickly as possible with as little hassle as possible. That's their job. I don't blame them for that. But our ability to potentially create an environment where then all of this other value can be added opens up all kinds of other opportunities.
Well, here's a question for you. So what discipline of engineering is involved with that, what you're talking about, visualizing these heritage mining landscapes and coming up with a concept of what best to do with them?
I have very close collaborators for those academics in the audience in mechanical engineering, in electrical engineering, in geological engineering, mining engineering, in environmental engineering, in environmental sciences, in business and economics, in ethics and civics, and we really, you'll see if you download our study, that it was very focused in, we wanted to under promise and over deliver, right? So we were very focused in the analysis that we did at Mather. It's the implications of that analysis that when you start to think as a bigger picture, as an heritage community about the potential, that's where it really starts to get exciting, and you're in totally new territory. The trick to this is that any community organization could download our first report, and they could look at what we did with the mining records, and then the design. There's some basic calculus and then some mathematical modeling that you can collaborate with a community college, a local technical college, like the sustainability program at Platteville is a wonderful example of a resource, right? Where you have very skilled people there who could help with that analysis. What we did in that way was not, it's challenging, but it's not out of the realm of possibility. And your community already knows a lot about, for instance, the environmental conditions in the mine and its consequences. They know about the geological and structural integrity in the mines and their consequences. So that there are, they have resources to pursue this kinds of study. And you could also email me. I'll be happy to give advice to any community group. I've actually been in a process now of going around contacting mining heritage organizations like this one and thinking about the nature of this moment in time and how unique and amazing it is. Because the opportunities there in the lead and zinc district are probably going to be different than they are here in the copper country. And they'll be different than they might be in California or in Arizona or in Florida, right? So that's a long answer to that question about scale.
No.
Just
Yeah,
because
no.
just because the underground mines, you don't really know the volumes yet, don't assume that it's not worthwhile to think about it, right? And as an example, the above ground mines, the lead mines are remediated, right? And they're encapsulated. But many of the solutions being looked at around the world, they're actually excavating a new lower underground reservoir, and they're going to build upper reservoirs on the surface of the ground. The reason being that if you build it, it's much easier to cost out the construction of the underground resource, and you can do it exactly the way you want it. So you don't have to refit things into, you don't have to customize them, right? It's the Walmart model, right? You design one and just build a bunch of them. And in these projects, these look like they're going to pay for themselves just with industry. And the idea that you might then redesign a land reclamation of the surface as a surface pond connected to a newly built underground resource, that might be something that the community might value as an asset, right? But maybe not. It's up to all of you to think about that. And industrial partners may be interested to pursue that. As you are like us, your location is between the Great Wind Corridor of the Great Plains, wonderful solar resources, and the population centers of the urban Midwest, right?
Yeah, next week we're going to have panelists representing some of our regional energy industry from Badger Hollow Solar, Renew Wisconsin, and the energy transmission industry, talking about some of the things that are going on here, renewable energy products, wind, solar. You have a slide, Tim, with a map of the United States, solar potential mines and existing solar power plants in the United States. And the Southwest Wisconsin is populated with lots of little brown triangles showing solar power plants.
Yeah.
But we're not showing, I think, because our mines maybe are not as deep as those up in the UP or southwestern United States. We don't have any little red dots kind of in our southwestern Wisconsin area, but we have lots of little other dots.
Well, and what I would say, looking at this national map, right, which I hope you're seeing that, Eric, let me know. Yeah, good. So this initial study, we used the United States Geological Survey minerals database as a jumping off point. And when we did our first run through of this map, like all of the UP's mines didn't show up on there.
Okay.
Because at the time when the geologists and the mining people who were compiling this data, mine depth was not a priority to them to record or document. So we identified challenges in the existing data. And so we've been going through and going back through that data to re-examine it now region by region and including Minnesota to think about what would it really take. We've got signed a cooperative agreement with the state of Michigan's abandoned mines program to take their digital version of their abandoned mines inventory and then re-examine it for these kinds of questions about adaptive reuse and energy, because it's going to require some investment of time to transform them. And I know Wisconsin has a similar sort of resource. As you look at this map, so please keep that in mind of how this is, I would say, grossly, it's inaccurate is not the correct word. It is more likely to have unknown unknowns in it, if that makes any sense. That we need, particularly for the older mines, we need more research to flesh that out. And again, a federal level agency isn't going to do that for southeastern Wisconsin, but you've got people who already know the data who could probably sort through that pretty quickly and find 10 probable locations that should really get looked at, right? Or depending on the model of whatever project you're imagining, they could say, here's where this mine is. What kind of project could we build at that mine, right? That's another perspective that people in agencies are not going to have, right?
Got it. Got it. Would you please flip to the very next slide, Tim? I think it's
Yeah.
the next one.
Um,
It's similar to this one.
Am I still sharing there? Can you still see
Yeah,
that?
yeah, that's
Great.
which is fine. But if you
Yeah.
make that full screen and then you see there, you see Southwest Wisconsin, there's a big density of all of those little brown triangles showing solar power plants.
And those are existing. Those are not the planned ones.
Got it. And
Yeah.
and as you said, Tim, it doesn't show a lot of our actual mines, but you see there's a
Right.
confluence there of all
Right.
that solar, and then it doesn't show the wind power, and then with these
Right.
mines. So then the $1 million question is, so what would our little mines be well suited for in the driftless region? And
I want to point out, Eric, on these maps, I didn't show you any that also have the electrical infrastructure overlaying it, where again, if you're thinking about it from this standpoint, a lot of these mines were big consumers of electricity, so that the electrical grids, as they were built out, were built to provide them with electricity, or in some cases, they actually were the first generators of electricity, right? And they were supplying it to their communities. But either way, there's often robust infrastructure already in place because it's still that legacy line that's carrying power. So all you would have to do is build this facility and just connect it often directly to the system, or maybe run a quarter mile to connect to the grid. Whereas if you were designing a new plant from scratch, it's at least $1 million a mile to run a transmission line, right? So if you're penciling out, this is the kind of detail I was talking about. If you pencil out the amount of money you save on electrical transmission, permitting, and building a line through the forest or across the prairie, and you count that as revenue against the added cost of building one of these facilities, again, they start to look really profitable.
wow. Okay, Tim, if you want to go ahead and stop sharing your screen for just a moment, we got another couple of questions in. Following up on your matter of these underground edifices, and whether an industry may want to have something of their own creation with a predictable shape versus having to retrofit into something that has some unknowns. Dina has a really great question, which, in addition to adaptively reusing historic mines, what about using caves? So here we are in the karst country. We've got lots of underground voids. Might they have any potential? Dina asks.
That's an awesome question, and the short answer with me is almost always I have no idea. In that, theoretically, yes, but I don't know about the geological stability, because once you're talking about this where you're pumping water back and forth, there's about the weight of the water, the vibration. You really need a professional mining engineer or geological engineer, civil engineer, somebody who can give you a quick read on that. But again, because we know that there are these other energy solutions, including compressed air, as an example, I would say it is worth asking questions, right? It is worth looking at. Now, a natural cavern, they are used for things like compressed air. Salt domes are used as an example for compressed air storage. But salt domes are fairly specific locations in the world. But as you imagine this kind of technology being adapted into those caves, it's entirely possible. Whether or not it makes sense is a question for, in my opinion, like a whole group of community volunteers and undergrad and grad students. You can get together in a room and be like, okay, puzzle this out, run numbers, figure this, do some stuff, show me the magic, baby, right? What does it look like? Because then they can start to give you actual answers of this is the energy potential, this is the cost potential, these are the environmental issues that would raise themselves. That's a terrible way to say that, excuse me. Here's a quick example, right? The mine water in Mather, if you were pumping that mine water, we know it is environmentally benign in terms of all the standards. And the same thing might be true of other mines in our area. But once you start pumping water around in the mine and you change the temperature and you change the amount of dissolved oxygen in the water and you change the flow of water, is that going to change the way that the water chemically interacts with the sides of the mine? Like, we don't know. No one has ever asked that question before. But now we're thinking about, these are things we can design as experiments to address that question to help with planning, right?
Well, and what you just said there leads to a question from Mark, in which he asks about what kind of geochemical constraints might be unique to our mines in the Upper Mississippi Valley District, where we had a sulfide component.
Yep. We are, I talk about this all the time because with our local audience, we do have problems with metallurgical pollution of the environment from our mine tailings. But I remind people that they are without belittling those problems, they are nothing compared to the problems of places that have sulfide ores and places that have heavy metals contamination and things like that. We do have metals as part of the issue, but again, compared to places like Anaconda or the lead zinc district, our troubles are not as significant, right? This is one of the things that is important to get out of the way immediately. The contaminated mine water is already there. It is already in the environment and it is already interacting, and it is, whether it is draining directly and discharging into surface waters, or it is slowly percolating through the groundwater and we pretend that it is contained in the mine, the contamination already exists. So in all the designs that we could come up with here, the key question is, can this design mediate or fix those problems, right? Can it make them better or not? Or will it make them worse? Because if it makes them worse, it's not a solution, right? And we shouldn't worry about it anymore. But can it be designed in such a way to make things better? And geochemical issues for the design are really interesting. That, again, another thing I have to remind people, mining engineering is incredibly sophisticated. We are really good at mining engineering. Hydropower, hydrological engineering is we're really good at that. We've been doing it for hundreds of years. And as a consequence, we have a pretty good idea of what the challenges would be and what the issues are. For example, you would, based on your mine water chemistry, its acidity, its salinity, and these sorts of things, plus its sediment load, you need to match the turbine design to the sediment and the chemical conditions to keep from corroding equipment underground during operation, right? But we know how to do all of that. It's just, again, no one has ever tried to do it in this situation before, right? There was a second aspect of that question, though. Could you remind me, Eric?
Oh, I think it was dealing with the fact that some of our local mines have a sulfide component.
Yes, right. Acidity and in addition, of course, lead and heavy metals are obviously an issue. Plus, I might add, all of the PFAS chemicals are a new concern that are out there on the table. People are concerned about that in the environment. And so as you're thinking about all of those issues, again, mining engineering and water treatment is a really sophisticated area of engineering. We are really good at that, setting PFAS aside, because that's a complicated story. It's never a question of whether or not we can treat the water. The question is, who's going to pay for it? How will we pay for it? I often explain or express myself about this in this manner. Would you rather have a facility operating on in this abandoned mining landscape where people are going to work every day, walking over the landscape, monitoring the water every day, keeping an eye on things for the next 100 years of the operational lifespan of this facility? Or would you rather have it be a field where stuff's happening underground that no one knows anything about? And I myself would be more comfortable with people being on site and responsible for those resources. We have a pretty good mine reclamation system, and I mean, there are issues in the US, but we don't have as much unregulated or unmonitored tailings ponds, for example, that are out around in the world, where, again, if I were a government agency, putting an industrial facility at that location where they could use that tailings impoundment as a hydropower asset, and also keep an eye on that tailings impoundment so it doesn't do anything it's not supposed to do, right? I would see that as a substantial non-monetized benefit, to put it into my business partner's terms, right?
Dina has got another great question. We kind of talked about using mines and other underground structures, and now she observes that in the Midwest we also have a different man-made resource, which are silos above the ground. She asks, how might silos be used? She's familiar with silo systems to raise fish. Might silos be incorporated to provide battery storage or some other non-transmission energy for communities?
Yeah, that's such an awesome question. And here's everything is changing so fast. It's so amazing. And the examples of other industries and technologies I gave you, those are all essentially deployment ready, right? There are operating demonstration plants that exist. There are all kinds of other technologies that are evolving. They're still on the sketchboard or they're in development. There's this great Spanish company, for example, called Magellan Barents, and they have a technology that they've developed because there were a bunch of unwillingly retired mining engineers and miners who were thinking about ways they could use their skills and their resources to revitalize the mining economy around Asturias in that region of Spain. And they had the idea of underground pumped hydro storage, but they took that idea a little bit further, and they've taken mine tailings from their area and reprocessed them into I swear I'm not making this up because they have patented this, so it is a real thing. What they describe as a super dense fluid, which means it's like a really muddy water. You would imagine it in your head, that it looks like paste, but it flows like water. And this super dense fluid, then, because it's got such density, in the same way that water is more efficient on a turbine than air, this fluid is more efficient in a turbine, so that you get greater energy density per volume. So you could take mine tailings out of the environment where they're contaminating things, reprocess them into this fluid, where then they were thinking you could put an energy storage system in an old industrial silo, right? A smokestack, where you could hang the system inside, and it would provide enough energy storage for some sort of new energy adaptation for that industrial facility, so that it could have solar power or be using wind power to operate and have a battery system contained on its industrial complex without having to have batteries. They have developed this to therein. Business people will understand the vocabulary, but it was something like they're at industry readiness level 7 and need to get to 9. But they're in that process of developing this prototype. And it's a perfect example of something that could fit within a silo, where you then can maintain the silo on the landscape as a visual anchor of public memory, while also providing energy storage as an asset to the community, and providing energy resources in facilitating energy use around that silo, right? That is a tech that's in development and is really exciting, but it still needs some understanding and some work. I'd be happy to put you in touch with those people if you want to talk to them. They'd be happy, like me, to talk your ear off about their great ideas.
Wonderful. Okay, so here's a question for you. You described what's happening in the United States as a huge fire hose of money heading our way to deal with this matter. And how might you advise a heritage site such as ours, the Mining and Rollo Jameson Museum, and we're a department of the city of Platteville, how might we position ourselves or Yeah, and what relationships might we want to build either with local universities or the State Geological Survey or industry or the other key players in this to try to benefit from this huge fire hose of money?
Yeah, yeah. And understand that the way this is working, the investments that came primarily through the Bipartisan Infrastructure Act and some of these other laws that have passed, um, the vast majority of those funds have gone into existing pipelines for development, right? So that they are being funneled through existing agencies, primarily the Department of Energy, but other agencies as well. And they are really looking, as government agencies will, at solutions that can be scaled and replicated, right? They want to show broad national benefit from any solutions that come out of public investment. And they're really expecting these investments to spark those demonstrations that will then make the rest of industry realize, okay, this is a good idea, it can be done, and then private money will flow more into the system to continue this transformation of our energy system. So that said, they are in the pipeline and they're going to try and solve the problem the same way they've solved the problem over and over and over again, which means that they're looking at big solutions that can be replicated. Now, this is a little bit different because of the way the Biden administration structured that law, or the Congress structured that law, and the way the Biden administration implemented it, that there are specific issues about social justice and environmental justice that are built into that calculator for figuring out which projects get funded in which areas, so that communities that have borne the burden of past energy infrastructure, disproportional, or communities that are economically vulnerable have increased access to those funds as a partner. But it's generally not going to go to like the city of Houghton or the city of Platteville, right? It's going to go to a big collaborative effort because they are going to try and spend $100 million over 5 years, right? I think that a wiser thing for the community to think about, your municipal leaders and I don't just mean elected leaders, but like all the leaders of your community, are really to think about the legacies of mining and legacies of energy infrastructure, and how they have how you have lived those over time, so that there are areas where people have seen advantages and people have seen disadvantages disproportionately, even within our own communities, right? People still bear the burdens of those legacies disproportionately. And to me, that's one of the first questions, because identifying those, and as leaders in your community, you know what those areas are that will rally large groups of supporters around them, so that then you know if we have a solution, it should touch on these things, right? Then at the same time, you can take the roadmap, and I'm happy to help with this, of how to evaluate the mines themselves, and start really examining them, crunching some numbers, and that anybody with any group of people who can get together who are familiar with local history, and who maybe you get somebody who has a little bit of GIS skill with computers, somebody who has a little bit of business and economic skill with project construction, things like that. I know your municipal and county governments have these people who could help to advise or directly be team members, right? It's absolutely possible just to start looking at these and think of them as potential assets, because then you can look at those places, and you as a community can think, what do we value about this place? What kind of vision would we have for what could be here, right? What does it mean if we could have stable energy supply and storage with predictable electric rates, and also essentially free geothermal energy for a heat pump for heating and cooling the facilities? Or what does it mean that this facility cannot be disrupted by, cannot easily be disrupted by some terrorist with an AK-47 who's just going to shoot out electrical transformers, right? Or what does it mean to our community if we were to have a facility where it's going to create a big surface pond and green space that you can't sail on because it, the water level is going up and down, but it creates a potential ecological resource that doesn't exist now. What might that look like, and how would we value that, right? Then I'd also recommend that you start talking to your local political leaders, not local, your state and your federal local people, right? Your House members, and make them aware of what you're doing, right? Because there's nothing stopping municipalities or regions or states from creating entirely new incentives to industry to say, you know what, we know it's a great risk to come in and collaborate with a community. It's hard to do, but if you do it, here's the economic benefit we're going to offer, whatever that economic benefit might be, direct investment or tax incentives, whatever those things are, we can make those, right? We, the democratic groups, we can do that if we choose.
Well, this is a subject that's deep and broad. I think it's got so much exciting content that is going to keep us busy thinking about and exploring for a long time. I think this is a real an exciting concept that connects the past to the future. It connects the unique aspects of place to questions of how can our place best offer something valuable to the people who live here. And this is in some ways it kind of reminds me of questions of organic farming or farm management here in the driftless area, which because of its hilly nature is not agriculturally well suited to some of the same kinds of monocropping and some of the flatter glaciated parts of the state. So we're no stranger to this idea of finding nuanced solutions to make the most of our unique landscape. Sounds like this might be a case of that. So we're going to have to put our thinking caps on, spend some more time with this subject. We couldn't be more delighted, Tim, that you reached out to the museum and make this friendship. I hope we will keep in contact and keep the conversation going. I'd like to thank you so much for spending the time to share your wisdom with our museum community, and thanks to all who have participated in the talk tonight. I'd like to invite everybody to join us again next week, Sunday, February 26th for Winter Lyceum 2 of 7, when the panel of regional experts present Mining for Energy, the story of Southwest Wisconsin's electricity journey. So thank you so much again for being here, everybody. Have a lovely rest of your weekend.
Thanks, everyone. Bye-bye.